Okay, I think we're going to make a start after the break. Hopefully everyone's got their fix of caffeine. So it's now my pleasure to introduce our first keynote speaker of the day, Vittorio Ferrari. So Vittorio is currently a senior staff research scientist at Google, where he leads the research group on visual learning. He received his PhD from ETH Zurich in 2004 and has been a postdoc at INRIA Grenoble and the University of Oxford. And between 2008 and 2012, he was an assistant professor at ETH Zurich, and at 2012 and 2018, faculty at the University of Edinburgh, where he became full professor in 2016, and is now an honorary professor whilst being at Google. And Vittorio's current research interests are in learning visual models with minimal human supervision, human-machine collaboration, and 3D learning, of which the latter he will present a nice talk for us today. So without further ado, I'll hand over to Vittorio. And yeah, feel free to begin.
Thank you very much for the introduction. Can you all hear me?
Yep.
Yeah, very good. So thanks for inviting me to this workshop. Was very pleased for this invitation and the opportunity to present my work. I am going to talk mostly about 3D deep learning, which is something I got into about a couple of years ago. And I think it's relevant to this workshop, given the availability of egocentric acquired videos, which presents great opportunity for 3D reconstruction and scene understanding. So the area I try to define it, what I really mean is that an image comes in or a video, and it passes through some system that contains a deep network, and we should get a whole scene 3D reconstruction. We should recognize every single object instance in the image with its class label and a 3D model, and we should try to understand what the spatial arrangement between the objects are, resolving occlusions. For example, here, we would like to find out that the chair is behind the table and reconstruct the hidden parts. Maybe figure out also semantic relationships, like the cup is supported by the table and the bottle as well. Above all, and this will be a big topic today, we want to have all the objects and all the common relative positions into a single generic coordinate frame, not separate object construction, but scene level construction. Another intertwined goal is to be able to draw new viewpoints given a single image or a small set. And beyond that, maybe we can do other edits, change the lighting in the image, change the textures, write something on the table that will be augmented reality. And these two goals are intertwined because in order to be able to do 3D, let's say, augmented reality well, you need to have some degree of 3D understanding of the scene. Here is some application. Indeed, imagine you have a chair, you would like to change its texture to another texture. It's very difficult to do it just by reasoning in 2D. The shading will depend on the shape, for example. Another application area is augmented reality, which I think is particularly relevant to this workshop, where imagine a user with an egocentric camera goes around and he sees aids projected on top of the real world. And robotics and surveillance, of course, need a good degree of understanding of the 3D world in order to take decisions and actions. So I've been working on two related strands of 3D deep learning, and these are 3D reconstruction. Typically today I will talk about the case of video. A video comes in and a full scene reconstruction with semantic 3D object comes out. And novel view synthesis, especially interesting in the case where you have a single image and yet you can draw new viewpoints of it. And more specifically, today I'm going to talk about the four, let's say, most recent works by my team. We wrote a lot more stuff, especially on the case of single image 3D reconstruction. I encourage you to check our website for those older works. But today I'm going to talk about four works. The first two will be about going from a video to a full semantic 3D reconstruction. And the other two will be about novel view synthesis by extending the very popular NERF framework. So let's start with the first one. Here, Vitocad is a work that we have online about since a year and a half. And the task is, given an input RGB video, you want to recognize all the objects, reconstruct them in 2D by aligning a CAD model into it. So you are given a database of CAD models, and you want to recognize the object in the image and find the 9 degrees of freedom transformation that will map that CAD model into the accurate position in the global scene reconstruction. And all the objects have to live in this single common coordinate frame. And the way we do this is to start by applying a 2D object detection algorithm, which also predicts an initial estimate of the object poses, and then track this object over time, and then integrate through multiple view constraints the measurements in order to resolve to get the results to a much better result, and getting to improve the estimate of all pose parameters, resolving the fundamental scale depth ambiguity, and resolving also occlusions for objects that go in and out of view. In fact, we base this on the Math2CAD framework that was invented by someone else, that takes a single image and output a 2D bounding box for an object, its class and score, a segmentation mask, and also a 2D prediction of the 3D object center in the image plane, and an estimate of the 3D rotation, only the rotation component of the pose, not the 3D translation and scale. And also produces a shape embedding that is used to retrieve a CAD model from the database that looks like that object. The problem with this, it looks like it's doing the whole thing, but from a single image, the Math2CAD algorithm resorts to sidestep the scale depth ambiguity. So it's very difficult to know how large an object is and how close it is to the camera at the same time, because these two factors are entangled and essentially geometrically undistinguishable from a single image. So in that paper, they resort to inputting ground truth object sizes and depths. So now we can do better because we have tracks of objects. So now we can try to integrate over time, over multiple frame measurements, to resolve the scale depth ambiguity and also to improve all the pose parameters and resolve occlusions. So there are many terms in our multi-view optimization in the paper, but I want to give a few core ones. So how would you be able to resolve the scale depth ambiguity? Well, what you can say is, if you hypothesize a potential pose in 3D, now, because you have the camera parameters, you can reproject this into the input views. And now, if you had guessed the correct pose, especially along the depth axis and scale, then when you project it, you should match about the spatial extent of the bounding box that you detected. And from a view, this can be done by cheating across scale and depth, but from multiple views, this cannot be done. You cannot find an accidental alignment. So, and that's why it can be resolved. You can also improve the 3D rotation objectives. Although it's possible to recover 3D rotation from one image, you can do better by hypothesizing a rotation in 3D and then saying that it should be close to the rotations predicted by the individual frames. And you can do the same with the translation objectives and so on. And this gives you a multi-view optimization system that you can solve over the pose parameters. Another way to solve the scale depth ambiguity that we also do is to extend the Math2CAD framework and say, well, try to predict the object size in individual frames, not based on recognition. So you recognize it's a chair and a chair has a certain size, try to directly output a metric value in meters for size. And now you can put a 3D objective that says the real size should be near the size of the individual frames. So if you do this temporal integration, you resolve scale depth ambiguity and you improve also all the other pose parameters. Related work, well, the biggest related work is point cloud 3D reconstruction from video, which has been researched, for 30 years and works very nicely. Here we want object level. And from a single image, there are a few works that are building blocks, but alone they don't get to 9DOF. And there is also a recent flurry of work, 3 or 4 works to which we belong, that tries to do this multiple object reconstruction from video. There was one that appeared before us, Frodo, which had just a few qualitative reconstruction examples. They wasn't quite mature yet to go into a full quantitative evaluation. And then concurrent to us, Molter and later Odam also managed to get to this multi-object reconstruction, and we compare to them in the paper. So if you follow the ScanNet, Scan2CAD kind of line of works, you might have noticed that there are several works that claim to be able to do multi-object reconstruction, but on RGBD scans. So here you have a Kinect sensor and you can integrate it with Kinect Fusion, and then you get a beautiful dense point cloud and fit your CAD models directly to it. Then it's much easier to do, but it only works if you have a scanner. So here are some qualitative results. On the left, you see the best result we could achieve out of the single frame Math2CAD after already helping it with this scale from recognition and introducing a 3D NMS to avoid duplicates. And pose parameter got out a lot better with our multi-view integration. Here is, no, that's the same video. Here is another example which can show that the beauty of doing things this way based on a detection pipeline is that you can have arbitrary number of objects. I find this looks particularly pretty when you have so many chairs. There are, I think, 35 chairs in this video. Here you can really see how difficult, because it messed up the depth estimate, the single frame baseline puts all the objects high up in the air, and the multi-view integrator resolves these ambiguities very nicely. So I said at the beginning of the talk, I care about global consistency and global maps. So you can do that by putting a camera on the ceiling and looking down. I mean, not a real camera, virtual camera, and draw the reconstruction as a map. And here you can see the map that comes out of our method compared to the single frame baseline missing a lot of objects. And here is the ground truth of the scan-to-CAD dataset. And these maps really get you a sense of how complex these scenes are in this dataset, and how many objects that are there. And it's really a challenge to reconstruct them all. Here, for example, there are two distinct tables that are identical in appearance, but they are distinct in 3D space, and you need to reconstruct both. So if we go for numbers, we can look at the scan-to-CAD evaluation dataset with its own appropriate metric. And the result to notice is that we almost tripled from 12 to 31. We almost tripled the ability of the single frame baseline to perform, although we build on that work. Multi-view integration helps a lot. And we also outperform a later work that appeared after ours called ODAM that follow a bit similar principles. So as I said, the dangling thing in this kind of evaluation is to say, yeah, but Vito, we have RGBD depth fusion maps for these scenes, so why bother? Well, the important point is to be able to do this kind of games without a depth fusion sensor so that you can apply to standard YouTube videos or videos acquired without a Kinect. So those works that acquire this nice, precise, dense map, they can directly fit the CAD models to this geometry, sidestepping all appearance, much, much easier. So we thought, what about we just apply CallMap, very popular multi-view stereo algorithm, and then we get a point cloud, and let's try to train these modern RGBD filters on this data. And we failed completely. We were a bit hopeless. But CallMap is no longer state of the art. So we went and dug, and we found the best available deep learning-based multi-view stereo method, and I reconstruct a much denser point clouds. And now, based on that, we managed to train a state-of-the-art RGBD fitting method by Matthias Inser's lab. And yet, the performance drop is dramatic. If you run such RGBD fitter on a nice Kinect Fusion landscape, then you get really, really good results. And if you run it even after training on these deep multi-view stereo outcomes, results drop dramatically. So in fact, VitoCAD is clearly the best work when given just RGB-VDS. So some of you might know that I like to do annotation. I released a lot of datasets in my life. And we extended this work now in an unpublished manuscript that we are going to release in a few months, where we have a human annotate just a few frames for each object, about 3, by clicking on point correspondences between a CAD models and a view. And then we pass it through one of these variants of this multi-view optimization, and we get 3D alignments. And this is cheap and easy to teach to the annotators, and you get great results. Like these are the ground truths for views of the same scene on ScanNet, and this is what we get with our technique, and they are basically essentially identical. They are over 95% accurate, and this will allow us to release for the first time a dataset that is composed of internet videos without depth sensors with perfect global scene alignments. Okay, this brings me to the second part, which is again in the same vein of trying to do scene level semantic 3D reconstruction, but this time with a more integrated approach. Let's have a look at it. So this one is called RayTran, and the permanent setting is the same. An input video comes in with its camera extrinsics, and you want to have 3D object detections and their a 9 degrees of freedom transformation to the global coordinate system. And those flurry of work I said that appeared recently, it's about 4, that are able to do to some degree this task. They all have one flaw, including our own VitoCAD. The problem is that they rely on a very complicated pipeline. So you have images, you need to detect objects in 2D, estimate some per frame properties, track the objects over time. That's very important. Otherwise, you don't manage to do the multi-view optimization. Then you can do multi-view optimization that integrates these 2D properties into a 3D estimate. And it's a natural pipeline, is the natural thing to do if you come from computer vision engineering, but it's extremely painful to handle because tracking by detection is super painful. It's brittle, you need to set it up, tune it, and every time you change the set, you have to re-engineer it. You cannot train the whole pipeline end-to-end, it's a bit annoying. So we thought, what about we trash the whole pipeline completely, and we try to do it into one unified neural network architecture. which is end-to-end trainable, it can reason holistically about the whole scene from the all views, but without needing any 2D detection and any tracking at all. Just try to reason as much as possible directly in 3D. And that's what I'm going to present you now. And it also allows you to minimally modify this architecture to get another function, which is not 3D reconstruction, but novel view synthesis. So here is how it works. No detection, no tracking promised. So you start by having these 2D views. And we want to output these 3D reconstructed objects. So now we can maintain two representations in parallel. So the first one is a two-dimensional representation that describes the scene from the perspective of the individual views. Imagine like a height with depth feature map. And the second one is a 3D representation that is kind of like a coarse, very coarse voxel grid of the whole scene. And inside one of these voxels, there is some sort of aggregated feature representation of the scene at that voxel point. So we can initialize this one by basically aggregating along the viewing rays that pass from the pixels through this voxel, aggregating all the 2D features that we have. So just to start. And we can initialize this one just by a ResNet. That's maybe trained on ImageNet. So now the magic of transformer comes. Now you can start to do 2D to 3D cross-attention transformer blocks to progressively exchange information between these two representations. And the output of the last block will be a 3D feature that aggregates the information from all the views, and it takes into account the context that is provided by all the views. So one of these voxel grid now contains an amalgamated feature that says what is the physical volume, the appearance of the physical volume in this voxel, as seen from all the views in context. And now you can come from this point and you can attach a 3D object detection head, maybe a 3D detector, that will then output, will count objects, output a global 9 degrees of freedom transformation, and also output a voxel grid that describes its shape. So now you can do end-to-end training from the end training data you have from scan to cut down to the pixels without passing by detection or tracking. And you can put losses on the object pose and on its voxelized shape. So to make it train better, you know, deep learning tricks, it sounds all very pretty and elegant, but to make it train better, we added two auxiliary losses. One is to global voxel occupancy. So just forget about object recomposition, just predict the full voxel occupancy of the scene. And also project this voxel occupancy into 2D, and it becomes a foreground background segmentation problem. And you can also put a loss on that. And everything can be done because we have an intrinsic parameter, so we can keep going back and forth. So now let me skip this one. So the transformer blocks are cool because they allow you to do this contextual reasoning and sidestep the tracking. But the problem is that if you want to have a big matrix where you list all the pixels and all the voxels, you are in something that's about 5-dimensional, 3 dimensions for the voxel volume and 2 for the image. And it's untrainable. It's just something like 50 gigabytes of memory, and it computes for, we never actually run it. I guess it will compute for weeks. So here is an interesting technical idea. You could say, well, we know the image formation process, and a voxel and a pixel are more likely to interact if they are connected by a camera ray. So if by shooting a camera ray through a pixel, you generate a frustum in 3D that you keep growing. You can follow it until you accumulate all the voxels that can be seen by that pixel. And then you can decide to sparsify the attention matrix to only compute attention between pairs of voxels and pixels that are caring about each other, that are visible. And this is a small simplification. In practice, most of the other entries are low anyway. And it cuts down your computational complexity and memory complexity quadratically. You go from, you know, cubic in the voxel cube size to linear. So that's definitely an important trick. So here are some results. Here is some bedroom, which has a lot of objects. Notice this video is a bit nasty because they're very close up. And so it's quite difficult to get a global sense of the scene. That also makes the task funny. And if you go forward, the same one video has a lot of objects, lamps, chairs, tables, and it's quite long. The scene is quite large. If you go into the toilet, we didn't have toilet bows, so it learns to predict a chair there, which is almost right. Here is another example. which is a scene I also had before from Vit2CAD. And if you place a virtual camera on the ceiling, you can look down and look at maps. These are the ground truth results, and this is what Retran produces, which is nice. It finds a lot of different objects in roughly the right relative arrangement. You can even reconstruct objects that are not in the ground truth, like this blue bookshelf and the yellow cabinet. I really like this top view map, so I drew a lot of them. Here you can see the ground truth and what Retran reconstructs on cases where it works well. Of course, it doesn't always work well. But it improves over the state of the art that I've shown you before, which was our own Vit2CAD, and now improved by another about 6-7%. And so this sets us a good 10% above any work that was done before until Odam. There is also another work called Moltar, and computer vision is they evaluate in another metric, and in our paper you can find a comparison in this other metric, both to Moltar and Odam, where both Vit2CAD and Retran win. So I promised that we can do other tasks, novel view synthesis, and we can. It's the beauty a little bit of a model that is so integrated with a neural network, much more than Vit2CAD and previous work. So we can run this whole transformer game till we get to this 3D blocky feature grid. But now, instead of doing data object detection in that 3D space, we change head. We can now put camera parameters for a novel view that are given to you. Somebody says, please draw me this scene from this new viewpoint. And from there, you can trace rays that pass through this 3D feature volume, right? That's easy because you have the camera parameter and the absolute volume of the scene. And now you can play the same game with these transformer blocks, but in reverse. This time, you know the 3D feature grid of the scene. And what you don't know is the 2D image features of this new view that you don't have. So you initialize it as empty or the average of the previous. Now you can start to cross-attention transformers to predict virtual feature map for this new 2D view that you don't have. Then you can decode it with a standard CNN decoder into the view that you have, and you can train now this system by having leave one view out on your training data, and it will learn to interpret the output feature grid and translate it or unproject it or decode it, whatever you like to say, into a new view. And it's really minimal. This is like 1 day of coding to get from a 3D reconstruction system to a novel view system. And we don't have a quantitative evaluation of this one, but we have some results here that I think it's particularly pretty. Here, these are the two closest input views to this target view. So these are the input frames. This is what Retran produced. And this is the ground truth, which we did not give to the system. These are held out views. And the nearest input view to this one is so far in geometry space that we don't believe that it would be possible to do a job like this without a model that's very 3D aware. Hypothesis. So I showed you now these two methods, which basically the second one, Retran, obsoletes the first, but from a historical perspective, that are able to go from a video to a semantic 3D object reconstruction where all the objects live in a common coordinate frame. So that sets me to the end of the first half of the talk. And now I'm going to show you a second part where we do novel view synthesis. So the first work is sharp, and I'm going to motivate it by telling you about classical novel view synthesis. So here you have multiple views and camera parameters of an object. And what you want to do is to draw new views. So the by far most popular way to do this thing since 2 years from now is neural radiance fields. And the way they work is you have a camera that looks at a scene. And for each pixel, we can cast ray that towards the scene passing through that pixel. And we can sample points along that ray. So for every point, we can pass the 3D position and the viewing direction to a neural network, a simple MLP that produces a color and a density at that point. So now you can accumulate, you do volumetric rendering, we can accumulate the colors weighted by the density along the ray, and this will produce a color for that pixel. You can repeat this for every pixel, and off you go, you have your image. So now, how do we train this model? This model is just multi-view geometry, or even more, volumetric rendering to be precise, with a little MLP in the middle. How do we train the MLP? The beauty is that you only need views, not the 3D scene to train. You only need pictures, because you can now sample all these pictures along various viewing rays, along the viewing rays, of the training cameras. You have your current model F, and you can now render the scene. And now you can simply put a loss that says, well, let's loop over all the pixels, and let's see if the color you produce with this procedure matches the ground truth color in my training views. And if it doesn't, gradient descent all the way, everything is differentiable, also the volumetric rendering. So this was a simple and great idea by John Barron and his team, and it's become by far the most popular way to do novel view synthesis in the last 2 years. It's great, but it takes a lot of views to work well, typically about 100. And sometimes you don't have that many views. Also, it trains a model for every specific new objects, and that will train for a long time. So can we do better and do NERF from a single view? Well, we are going to be able to do it, but because we don't have enough multiple views, we don't have any multiple views to build the radiance field properly, our new idea is to construct a geometric scaffold to condition the whole rendering process. And so this is our overview of the system. And we can see that we can formulate image synthesis as a generative process where we estimate the 3D shape of the object within our network, and then we use it to guide the radiance field function. So the appearance network contains this radiance field function, which in addition to receiving this 3D voxel grid predicted by the network, also is conditioned on an appearance code. And this appearance code controls the shape and textures of the particular class you train the model for, like chess. And this allows to model this variability and make it generative. So the whole process is invertible, which means that if you are given a new object with a new picture, you are able to differentiate through it, recover the appearance code and the shape code, and therefore interpret the new image. And then you can run it again forward, provide the shape code to this NERF block, and draw new views. So let's see how it works in more detail. So the shape network represents a mapping between a shape code and a voxelized shape here. And we can train it in a supervised way simply by directly predicting the voxel grid that you have for training with weighted binary cross entropy. Normally, you can have a symmetry loss term that says chairs are symmetric along the vertical axis. That helps, doesn't matter too much, but it helps. And then more importantly, you can have a silhouette loss, which you can estimate by drawing images from 3 projections of your current voxel grid. And that helps, to say, solidify your loss and make it stronger. So during training, we can train both the shape code and the network parameters with the GLOW framework. The appearance network is similar to NERF, but we can have additional input. Normally, you pass a 3D position of a point and a viewing direction. Now we can also pass, this is the real novelty of our work, we can pass the occupancy predicted by the shape network, and also an appearance code that we can say controls shapes, controls appearance, basically. So now we can train the model end-to-end to re-render the training images, like in normal NERF, with a loss on the pixel colors. So now you can train this model, and at training time you have 3D, and you also have multiple views. And now at test time, you only have one new view of a new object, no 3D, no multiple views. But to simplify the problem, we give a segmentation mask and camera parameters. So now in the first step of inference, we retrieve the shape code. We search for the shape code that would re-render the silhouette of this object. And during inference, we update both the shape code and the network parameters, because this results in better reconstruction. We can also optimize over the camera parameters, which we will show in the next slide. So here we compare optimizing only the shape code or jointly with the network. If you optimize only the shape code, the results are a bit blobby. Together with the network, it gets crisper. So we can adopt a similar approach for the appearance network. Given the voxels you had in the previous step, you can find the appearance code and the network parameter of the appearance network that re-render the input test view as well as possible. Again, it's better to optimize both the appearance code and the network parameters jointly. It gets much better. So if you want to render a novel view now, you can trace a path, place a camera, cast array for every pixel, and render its color with the model. So related work, there is 2 kind of groups of related works that are close to us. One is generative models that try to condition some neural rendering process on some latent codes that represent distribution of appearance and shapes of classes. And in a second category, there are works that are more about extracting image features from the input views, like 2D features, like classical, and then condition a rendering process on these features. And these processes are not generative; they cannot make new objects, but they can render new views given a new image. And 4 of these works, they are particularly positioned as NERF from a single view or NERF from a few views. And they all share the characteristic of training a class level model for NERF, just like we do. And Graph here and Seren wouldn't count there because Graph is not able to render new views given an input, just generative, and SRN was pre-NERF, so it doesn't belong quite there. Now, it's a fun field to work on. It's so dense that if you look at when Sharp was published, in a radius of like a few months around it, there were already 3 works that were kind of single or few shot NERFs. And several months later, another one appeared by UCL, CodeNerf, which is the closest in system, but it was later. So here are some results. Here is the model is trained on ShapeNet cars, and the novel views are estimated given only the single image on the left. And we use the simple rendering synthetic of the SRN paper. Now we can see that given a single test image, we can reconstruct and re-render the object from views that were hidden parts, which shows that the learned priors are actually working. And if you go to the paper, you can find a quantitative evaluation showing that this is state of the art on this data set around par with PixelNerf. For chair is fun because we can see the 4 flag that is not visible in the input image can be successfully reconstructed thanks to the priors. Also, now we can go a bit beyond and we can generate a new test set where the objects are rendered with more complex lighting and in higher resolution. And our method is able to generate accurate novel views, even if it was trained on simpler data, which shows that we can generalize beyond the training domain. And this we achieve because we optimize both the latent code and the network parameters. And a bit of the same game on an even more impressive, I would say, on Pix3D, real images, not synthetic. With a given segmentation mask, we can now, trained only on this simple rendering of SRN, we can now, just with a single test image, we can now synthesize new views for these objects. PixelNerf, as I said, is the most related work to ours. It's also appeared about at the same time. And what they do nicely is that they manage to do new view synthesis from a single view without needing extrinsic camera parameters at test time. So we extended our method to automatically estimate camera parameters. It's quite easy in these images, and then did a comparison. And what turns out is that because PixelNerf operates in view space, it has a lot of trouble in rendering things very sharply along thin structures, and that generates this kind of blur. In the paper, we explain this a bit more. So we get to the last piece, Urban's radiance fields. So far I was trying to do the magic of rendering new views of a single object in rather controlled conditions, given a segmentation mask. Now we can go more in the wild and try to operate on street view data. So normal urban radiance fields, they are in this controlled environment with a nice closed full dense camera path around one object. And now can we do it for large outdoor areas like in street view? So the street view data is captured by a tracker, which is a system which has 7 cameras capturing panoramas about every second. And there is also a LiDAR sensor, which provides very sparse but really accurate point geometry. And a tracker run is some guy with a backpack wearing the tracker and going around and running around the square. And we take these views and we try to generate continuous camera paths that's much denser than what you can do now on street view. Now on street view, you can only travel along the acquisition path, which is only, one viewpoint every second. And you're on rails, you cannot move off that acquisition path. So there are 2 groups of related works to this mission. The first is a work that try to patch together several NERFs so that they can cover a much larger area. We don't do anything in that direction, that would be kind of complementary. And then closer to us is works that incorporate depth supervision into NERF. In particular, DSNERF, who runs a SFM pipeline to get point clouds and try to use those to help NERF training. And this other paper, neural RGB reconstruction, which uses a Kinect sensor, which is very precise, very, very deep in indoor settings, and uses also data supervision. And in the paper, there are more detail, but we propose new depth supervision losses that work better, that we demonstrate, than those in those papers. So maybe I skipped on the background on NERF. We saw it before. The way it works, you cast rays across your training views, you sample the rays, generate an image with an MLP, perform volumetric rendering, and in the end, you can train it for re-rendering its own training views. So the way we extend vanilla NERF is by adding LiDAR supervision, which helps getting much better geometry estimation, compensating for auto exposure and white balance, because these trackers, they go around with auto white balance, and as the luminosity of the scene changes or you just go around a corner, the camera starts changing the global tone of the image. It gets towards green, towards blue, brighter, darker, which confuses NERF a lot. And we also model the sky because, as we see later, NERF is not good for things that are infinitely far. So let's open each of these contributions in turn. LiDAR supervision, from a physics standpoint, a LiDAR point is a solid surface point, which means that the density should be high near the LiDAR point. It should be 0 before, and you don't really know what happens after the LiDAR point. There could be another object, there could be nothing, you don't quite know. So now we can formulate 3 losses to exactly capture these physical rules. First loss is the near surface loss, which is also the most innovative compared to previous works. Here we encourage high density near the LiDAR point. We have a margin around the LiDAR point, and we say the density predicted by the NERF should increase rapidly towards 1 in this margin. The margin is there to model the natural Gaussian noise around the exact acquisition point of the LiDAR. So before that margin, the loss should say, please put empty space there, have very low density. And on average, which is also a loss used in previous work, on average, over the entire area, you can compute the expected depth according to the NERF, and that expected depth should match the LiDAR point. So in the paper, we have various sophisticated ways to combine these losses, in particular, a particular marginal leaning schedule that's important to get results good, but I skip in this talk. So the second contribution was to compensate for exposure, because again, people go around with auto exposure, auto white balance. So the same physical structure can have different colors in different images. So previous work have noticed this, like NERF in the wild, and they tried to have very generic latent codes that allow a bit too much freedom. They allow different parts of the image to change in different ways, in ways that are not physically justified by auto exposure, and these generate artifacts. So our solution is to have a much more restrictive transformation. We estimate a single global color affine transformation for each image together in the same neural network, and then every pixel in that image I have to use that affine transformation, which is a good model for auto exposure and auto white balance. So sky modeling is important because if you shoot a ray to the sky, it should have 0 density, but NERF really wants to give it a color, and it cannot give it a color if it has 0 density. So this leads to crazy ghosting artifacts and floaters, dust in the middle of the reconstruction.
We have a couple of minutes left before
yes,
questions. Yep.
Absolutely, indeed. I plan to finish in a couple of minutes.
Okay, great.
So here what we changed is not to make it predict density, but instead model the sky appearance directly. If you're pointing to the sky, directly get a color. And to do this, the model is much simpler, and it doesn't need to predict density. And it requires off-the-shelf semantic segmentation to decide which pixels should take the sky loss and which pixels should take the normal loss. So here I get to results. We show results on 10 cities in 5 continents, which is very exciting. It's very broad. Things we can do thanks to Google Street View data. And I'm going to show you quantitative analysis on 4 cities. So MIP-NERF is the work we start from. If you add the exposure modeling and LiDAR, everything gets much nicer and photometrically consistent. And if you also add LiDAR, then these results on the arcades get much better, because this distant point benefit from having geometric supervision. Here are fun videos on novel view synthesis, walking through this scene. You can see you can really get, here we can show the acquisition path of the tracker and how the red point is the current viewpoint. You can see we can go far from acquisition path, up to 5 to 10 meter away, and this gives a much nicer street view experience. Here's another example. This is Zurich, actually, near where I live. You can also place synthetic objects into scenes. This is in Seattle. And maybe accelerating a bit through the quantitative evaluation, basically starting from MIP-NERF, which is the base work we start from, adding exposure and scale modeling, results get much better in new view synthesis, and adding LiDAR even better. We also took the S-NERF and gave it LiDAR points instead of SFM supervision, so that we could have a baseline that is a bit like in our spirit, and it still underperforms. So here are results for depth estimation. To conclude, you can get these depth estimates directly out of the NERF by computing expected depth. And from MIP-NERF, the system we start from adding LiDAR gets these nice results in the distance. So I mean, adding exposure and sky modeling, and adding LiDAR gets these results in the distance better. And you would say, why don't just use LiDAR? Because LiDAR has weird scanning patterns that results in holes. Maybe I skip over this and over this, and I show you that we can get 3D reconstruction results for multiple cities. And in terms of number, everything gets better thanks to the 3 contribution I described. You can also get colored meshes by getting colors out of the networks and adding them to the meshification, and then you can render them in your browser. So this brings me to the end of the talk. In addition to the deep learning, I also work on transfer learning, and you can check my website for such kind of works.
Okay, we have a couple of minutes for questions. If anyone wants to ask, go to the microphone.
Right. Thanks for the talk. I think you might repeat the question. So, because one of the issues we have with egocentric is the fact that the person manipulates the scene, right? If you go there and you're doing something, you're sitting on the chair, or you're actually doing more than just observing. How far do you think we are from attempting to do 3D while people just walk into a scene and basically carry out their daily lives, prepare a meal or to eat, etc.?
Okay, so I'll repeat the question just in case you
Thank you, because the audio is terrible.
Yeah. So in egocentric, people are moving around, interacting, sitting down, and we're not just kind of observing the scene. So where do you think the gap exists, or the gap exists, but how do you think we can kind of close this gap and have a way of allowing for people to move around and interact with the scene?
Yeah, so I see 2 big problems moving from what I've shown to something that works in your setting. The first is that the scene is dynamic. So people go around and move the chair and drink the coffee. And a lot of these things require, I mean, NERF itself is extremely requiring that the scene is reached. And then the second problem is that you have hands in the view. I looked at a lot of this that is so annoying to our designs, and maybe also so interesting, right? That makes it a field. I think it's very exciting that you guys look at transfer. So I think that there are many ways forward if one really wants to do these kind of things, on egocentric data. But I think the most important part would be to be able to separate the scene into components that are rigid and stable over time, should be the majority of the 3D volume, and things that are continuously variable. And I think that doing that online while the camera is acquiring is an extreme challenge. I really have no idea how. However, if we are a little bit more humble and we say, okay, we have the full video till the end of the session, done cooking, or then we could start thinking about a model that has a notion of layers, of things that are rigid and static and things that are dynamic. And I think there it would be possible, for example, to allocate different rigid models to different components of the scene and doing it in an offline process.
Okay, thanks. Does anyone have any other questions? Okay, maybe I'll ask a quick question. So in the first work, you showed how much kind of depth improved one of the models, and kind of there's even with depth, there was kind of a gap between the proposed work of yourselves and kind of that model with depth. So just wondering if you had some comments on how to reduce this gap, if there's any intuitions that you might have for future works.
So we're talking about the very first work, right?
Mm-hmm.
Yes, absolutely. So this was a comparison of using only RGB videos compared to having Kinect Fusion, which is the normal way to solve that problem on scan to cut. There is still a gap if you are able to have that. It's another 8% better or so. So the real issue is that, the real benefits of having Kinect Fusion is that you have extremely dense 3D points, even on rather small objects, especially in these videos where the camera comes so close to the object and goes far away, very good for Kinect. So I think that in the future, to get those things right, when, you know, I skipped on a lot of ablation, but where we fail purely RGB is on small objects. It's lamps and TV screens that are on top of a bigger object. And there, it's not so easy. It's always this problem in computer vision with resolution and depth. I think we should get even better at detecting objects. I mean, this is like the classical 2D problems, or even better at context. So in our work, we didn't try to reason of the type, well, there is a table, and a table typically has a screen on it, and this data set. We don't have those priors, right? And which those priors have been shown to be quite useful in the 2D computer vision community. So that could be a way to go, to be attention to smaller objects in some way, but also perhaps compensate for things you don't see so well by having contextual interactions.